Okay, remember we had a nice property of the linearity. So if we if we took the Laplace transform of AF plus BG, that was equal to A times F, the Laplace transform of little f, plus B times the Laplace transform of little g, or we'll call it big G. So that was one property. Now we also have a great derivative property. And we need integration by parts to see this. So suppose we say that the Laplace transform of little y is uppercase Y. Okay. So if we have that, then let's look at the Laplace transform of the derivative of y, y prime. Okay, by definition, that's going to be the integral from 0 to infinity of y prime of t e to the negative st dt. Okay, so we have that for our definition. Now, to integrate this, well, we're going to need to use integration by parts. And so remember, with integration by parts, we have something that we tend to think looks sort of like u and dv, where that's a derivative and that's some function, and so, well, what better to use for the derivative than the y prime? And so with integration by parts, we integrate that part, the dv. Well, that's easy enough. The antiderivative of y prime is y, so we get our y of t e to the negative st, and we have to evaluate that from 0 to infinity, or look at the limit as we go to infinity. And then the integration by parts says then we subtract off that v times du. So here, this first part, we had our uv, and then it's minus the antiderivative, or, well, definite integral in this case, of the y here times the derivative of e to the negative st with respect to t. And so, well, when we take that derivative, we'll get an e to the negative st, but then times negative s. Okay, and this is a minus, so this ends up being a plus. Well, we can put the s out here, so plus s times the integral from 0 to infinity of y e to the negative st dt. Now, when we put in infinity up here, well, what we know is, well, that should have been a y of t right there, but I guess we know that. Back here in the first part, we need to plug in infinity. Well, we get y of infinity times e to the negative s times infinity. Well, we don't know a lot, but we know that that must go to 0 because the Laplace transform of y exists, and we see the Laplace transform right there. So we know that that must go to 0. However, when we put in 0, we'll get a minus y of 0 from this first part, and then plus s times the Laplace transform of y. Okay, so that's our property, is that if I want to take the Laplace transform of the derivative, actually, I can write it as s times uppercase y, where, as I said up here, that's just the Laplace transform of y, little y. So s times uppercase y minus y of 0. So there's another big property. Now, if you continue that, I mean, if I can do it with one derivative, why can't I do it with two and do more of these and just keep using integration by parts? Well, you can, and what we have then is if I want the Laplace transform of y double prime, that turns out to be s squared times the Laplace transform of y minus s y of 0, and then minus y prime of 0. Okay, and it just keeps going up, and so if I had the Laplace transform of y, and now I'm going to put this k in parentheses, which means it's a derivative, not a power, and so if I need to do that, well, the pattern is we have s to the k times the Laplace transform of y, and then we have minus all these derivatives and the function itself, so we have s to the k minus 1, y of 0, s to the k minus 2, y prime of 0, and we're just going to keep going until we finally get down to minus y, the k minus first derivative at 0. So you see, for initial value problems where we are given, say, a differential equation, you know, so like a second order, like we might have that second derivative, remember that we're then usually told what y of 0 and y prime of 0 are. Oh, so we would know those two values, and so this turns out to be the amazing property that will allow us to use this particular transformation to solve differential equations. Okay, so it's all about this derivative property, and it's got a nice pattern to it. You know, to tell you the truth, I don't know that I always remember it, but notice what's happening is if this is the kth derivative, we take s to the k times that Laplace transform of y, and then we just ladder down the powers of s all the way down to 0, s to the 0 at this last one. So we ladder those all the way down, and we ladder up on derivatives of y. Okay, so the powers on s go down, the derivatives on y go up. And so, you know, that's one way to remember it. You know, it's always there in your textbook. You can write it down, that sort of thing. You can look it up on the internet, and so it's there. But it's not that bad to remember either, if that's what you want to do. So that's an introduction to some more properties. So introduction now. That's just some more properties of the Laplace transform, and we'll use that then to solve initial value problems.